Hello, water managers. My name is Andy Richter, part of the Water Management Systems Division at the Hydrologic Engineering Center. I'm going to be covering HEC-RAS for swims today. This presentation is part of a series of recordings that will cover various topics relating to HEC-RAS modeling for swims. There are 6 main topics that will be presented in this series. Video number 1 covered the first 2 topics. This video will cover HEC-RAS program essentials. Let's get started. This is the main window you will see when you open an HEC-RAS model. There are 3 main components of an HEC-RAS project: the geometry files, the flow files, and the plan files. The geometry files physically define the river system being analyzed. The flow files contain boundary conditions for each river reach. In this example, the model is using the unsteady flow option. The plan files combine one geometry file and one flow file that will be used for the model compute. You can have any number of plan files, geometry files, and flow files within one HEC-RAS project. Now, we will look at each of these components in more detail. The geometry files are the main component of any HEC-RAS model. They can be as simple or as complex as you need them to be. There are many different options available within the geometry editor that allow you to add elements needed to define your river system. The first element is cross-sections. Cross-sections represent the geometric boundary of the stream, the channel, and the floodplain. Next are bridges and culverts. Another element you may encounter is inline structures. Inline structures are used to represent dams, weirs, or spillways that fall within the channel and impede flow. Lateral structures are another element that can be included in your model. These typically represent levees or embankments that separate the main floodplain from off-channel storage. The last element type that we will cover in this presentation are one-dimensional storage areas and two-dimensional flow areas. One-dimensional storage areas can be sometimes referred to as bathtubs because when water enters the storage area, they fill up like a bathtub and have a flat water surface elevation across the entire area. Two-dimensional flow areas are represented by a mesh, as shown in this figure, and allow water to flow through the area depending on the underlying terrain. Terrain data is an important component of any HEC-RAS model. Terrain data is used to develop the geometry data that we just discussed, such as station and elevation data for cross-sections, lateral structures, bridges, and so on. Terrain data is also used to compute elevation storage curves for any one-dimensional storage areas. It is also used to develop the computational mesh for two-dimensional flow areas. You can have multiple terrain data sets within your HEC-RAS model. One terrain may have a very detailed resolution, like a 1-meter grid, for example. This detailed data will be good to use when developing the geometry file. You may also want to have a coarser resolution file, such as a 10-meter grid, to use when developing inundation maps. The larger grid cell size keeps the file size of the outputs more reasonable. HEC-RAS models can't run without boundary conditions. We need to tell the models where the water is entering the system, how much is entering or leaving, and when. This information is entered into the flow files. For SWIMS models, the 2 primary inputs for our HEC-RAS models are going to be outputs from HEC-HMS and HEC-RAS-SIM. Remember that HEC-HMS provides runoff flows into the river system, while HEC-RAS-SIM provides releases from any reservoirs within the watershed that are being modeled. Your model may also include other types of boundary conditions, such as observed or forecasted data from tidal gauges, outputs from other SWIMS HEC-RAS models, rating curves, or normal depth slopes. This image is an example of the unsteady flow data editor that you can find within HEC-RAS. This is where you define the boundary conditions needed to run your HEC-RAS model. The image on the right depicts our HEC-RAS model geometry. As you can see in the upper left corner of the image, there is a reservoir that is discharging into our system. This output would come from the HEC-RAS sim model. We also have HEC-HMS outputs from subbasins that enter the river at various places downstream of our reservoir, as shown here. Now that we've talked about geometry files and flow files, let's talk about the third major component of an HEC-RAS model, the plan file. In broad terms, the plan file controls the simulation. It combines one geometry file with one flow file, sets the time window, defines the computation options and output options, and most importantly for SWMS users, becomes the HEC-RAS model alternative when imported into the cavity. This is an example of an unsteady flow plan. This portion of the dialog defines which geometry file and which flow file will be used for the simulation. You can choose which files to use by selecting a file from the available options in the drop-down lists. Here's a simulation time window. For SWMS forecasts, this data will be replaced with the start and end time for the forecast when a new forecast is created in the cavity. These are the computation settings for the plan. You will choose the time step or computation interval for the run. In this example, it is set to 1 minute. You will also set the time intervals for various outputs. These settings have been preset when the models were developed, so you should not have to adjust them when running a forecast. One other major component of the HEC-RAS software package is RAS Mapper. This can be used to develop a new HEC-RAS model, view model output and compare results, and develop inundation mapping products. For SWMS users, most of the time you spend using RAS Mapper will be to develop inundation maps. Once a run has successfully computed, you can display GIS outputs, such as the inundation depth grid, to determine what areas of the floodplain will be flooded and how deep the water will potentially get. You can animate outputs to see how the inundation changes over time if you are running an unsteady flow model. This can help determine when areas will start to flood or when the floodwaters might start to recede. It is a great tool to use when demonstrating to others in your office the results of your forecast. Here's an example of an animation created using RAS Mapper. You can see the floodwaters start to inundate the floodplain, and as we zoom in, notice the depths begin to increase in the overbank areas. The grid shown on the screen indicates that this model has a two-dimensional flow area. These types of animations can be helpful when trying to relay information to emergency managers, first responders, or others helping during the event. The video animations are a great way to share information to others in your office. But if we want to share information from HEC-RAS to other models, such as HEC-FIA, then we need to create stored maps. Stored maps are results that are exported as a GeoTIFF raster file and saved on disk. This allows us to get the computational results from HEC-RAS and either make a map using GIS products or run HEC-FIA to compute consequences. If you have any other questions about our software, need some help, or are looking for additional training, check out these links. They can also be found in the description below. Thank you for your time.